Hello everyone. In the previous video, we learned how we can design the circuit for a gated SR latch, and we derived the state table of the circuit, showing what will be the next state when the gate is disabled and then when the gate is enabled for all different combinations of S and R. So in this video, let's simulate the design to make sure the output will be as expected. It's always smart to simulate your design first before actually building the actual hardware. So this way we can catch any mistakes early in simulation and make the appropriate correction if there are any mistakes before we actually move to building the hardware. This way we can save money and make sure the model working as expected. So let's build this circuit, simulate the design, and check what will be the next state compared to the current state. So we need a couple NAND gates. We can go to the library browser and get the NAND gates, or we can click anywhere in the Simulink and just type NAND. So this will be the NAND gate we will use. And we need 4 of that. So let's make some copies. And then let's design these two. So the output from here will be the input for this NAND gate, and the output from the bottom NAND gate will be one of the inputs to this top NAND gates. It doesn't matter where we connect it, but let's keep it at the bottom here. And then the output from this NAND gate will be the other input to this NAND gate, and then the output from this NAND gate will be also the input to this NAND gate. And then for these two NAND gates, we have the set is one of the inputs to this NAND gate, so let's get some input ports. This will be set. And then we can make another copy, and this will be our reset here. And then those two inputs will be connected through a gate. So let's get another input port. This will be our gate. Then we can connect it to both of these NAND gates. And then on the top here, we'll have our Q state and then a Q bar or Q prime. So let's add some output ports. So this will be our Q. And then at the bottom here will be our Q bar state. Let's call it Q prime. So that's it. This is the circuit. Now we need to simulate the design. So before we do anything, let's create a subsystem. So we can select everything, go to Modeling tab, and create subsystem. Let's resize it. And then if we want the gate to appear in the middle, so we can go back in it, and then we can renumber it to number 2. So in order to simulate our system, we need to apply some inputs to the set, gate, and reset. So for this, I created this. So in this scenario, I have the set in this shape. And then I have the reset in this shape. And then I'm doing 0 to 16 seconds. The reason for this, I will simulate the system between 0 and 8 when the gate is disabled or equal to 0, and then I will check the results from 8 to 16 when the gate is enabled. For every 2 seconds, for the first 2 seconds, we see the reset is 0 and also the set is 0. And then for the next one, when the set is 0 and the reset is 1, and so forth. So we can see all of these 8 combinations in the simulation and check what will be the output. So going back here, so we can just connect the set to the set input, the reset to the reset input. So simply we can do this, and this is the reset. We'll connect it to the reset input. And then for the gate also we need some input. We need to test our system for gate equal 0 and gate equal 1. So let's have some step input. And then as we said, we can, the step time, we want it to step from 0 to 1 at 8 seconds. And then to step from 0 to 1, from disabled to enabled. And then we can connect this to our gate. Now to visualize the outputs, we need some scope. So we can add a scope. And then what we want to see, we want to see 5 things. We want to see the set, the reset, the gate, the Q state, and the Q bar state. So we want to see 5 inputs here. So let's see. So first we need to see 5 input ports. So that's 5. And then let's see 5 sub windows we can do like this. So this is ready. Now we just need to connect. So let's start by this order: G, S, R, Q, and Q plus. So we can use some GoTo, or we can connect directly. So let's learn about the GoTo block. So this is the set. We can call it set. And then we have another GoTo block. This will be our gate. And then we can create another copy of the GoTo block connected to the reset. And let's change the name to reset. And then also another one for the Q state. And then if we want to see the complement of Q, we can also plot it. So let's call it Q bar. So that's it. Now we need to connect these to the scope. So we start from the gate. We can just, like when we see this little arrow here, we can left click and drag it. So this will create the from block. Another way to do this, you can create a from block, double click on it, and then choose the name. So if we want it from the gate, you can choose a gate, but it's easier to do it the first way I showed. So this is our gate. We want it to appear in the top subplot in the scope. Then next we want the set. So we can do the same thing, hover over it, drag this little arrow. Next we want the reset. Next we want to see the Q state. And then lastly the Q bar, which is the complement of Q. Now we can type on the signal wire here, we can type gate or G. We can type the set. This is our reset. This is our Q state. And this is the Q bar. And the reason I write it here on the signal wire, I'll show that in the scope in a little bit, but it's easier to visualize in the scope. So that's it. Now we need to, because we set our input to 16 seconds, let's set the stop time to anywhere 16 or above. So 16 is enough. And then also let's go to modeling, click the gear here. And then we have, by default, Simulink is set up to variable step. So in this way, let's do fixed step. And then the step side, let's choose something small. So 2 milliseconds or so. And then we can choose discrete or ODE4. So that's it. Now if we run the simulation, it will create an error. And we mentioned that in the previous Simulink video, because we don't know the current state of the system. Is it 0 or is it 1? And let's show that. So if we run the simulation, we will see an error. So the way we fix this, we need to have an initial state of the system. Q could be 0 and could be 1. And to do this, we can use a memory or delay block. So unit delay, wait for Simulink. So this is our unit delay. We can resize it, and then this will connect it to the Q state. And then now we can apply initial condition. By default, it's 0. So let's first check the system when the initial state is 0, what will be the next state, and then we can resimulate for the initial state 1 and check also the results. So now if we run our simulation, it should run without an error. So that's it. Now we can double click the scope and then we can check the results. So that's what I mentioned. It's better to write the signal name on the wire here, so we can see in the Simulink, so we can see what we wrote. We wrote a G, we wrote set, reset, Q, and a Q bar. So there you go. Actually, it's better we can overplot Q and Q bar and just do this. Instead of 5 subplot, let's see 4. and then we run the simulation, and then we can view the legend. That's it. So Q is in the yellow and Q bar in blue. We can definitely change these colors. The way to do this, we go to View, Style, and then we can choose which active display. So we have 1, 2, 3, 4. We can choose number 4, and then we can change it. So let's see the Q in size 2, and let's have it as green. Looks good. And then now the Q bar, we can select the drop tier, select Q bar. We can choose also 1.5, and then we can select like dashed line instead of straight line. It'll be easier to see both states. So now let's check our results. So from 0 to 8 seconds, we have a G is disabled, as we can see here. So we're looking in these like first four rows. So when S is 0 and R is 0, as we said, the initial state of the system is 0. So when S is 0 and R is 0, and this is between 0 and 2 seconds, we have S is 0 and R is 0. So what is the next state? Q, the next state is the same as the initial state 0. And then from when S is 0 and R is 1, S is 0 and R is 1 between 2 and 4 seconds. We see also we're holding the previous state. It's remaining 0. From 4 to 6, we have the set is 1 and the R is 0, as we see here. Also, we're still holding the previous state. Last row is S is 1 and R is 1, and that's between 6 and 8 seconds. S is 1, R is 1. We're still also holding the previous state of the system, which is 0. Now moving to enabling the gate at time equal 8 seconds. So we're enabling G is going from 0 to 1. So let's see what happens. Now we're going to validate the next bottom 4 rows. So first, when S is 0 and R is 0, that's between 8 and 10 seconds. We have S is 0 and R is 0. So we see that we want to hold the previous state of the system. It's remaining 0. Next, when S is 0 and R is 1, so S is 0 and R is 1, that's between 10 and 12 seconds. S is 0 and R is 1. So we're setting the output to 0, and that's remaining 0 here in green. When the set is 1 and the reset is 0, the next state should go from 0 to 1, or should go to 1, regardless of the previous state. So that's what we see here. So between 12 and 14 seconds, we have the set is 1 and the reset is 0. So indeed, it's going from 0 to 1. And then a Q bar is the complement of it. Q bar is going to 0. That's what we see here. And then lastly, when S is 1 and R is 1 and the gate is enabled, we have our invalid state. So from 14 to 16 seconds, we have the set is 1 and the reset is 1. And then we see both Q and Q bar are both 1, which is invalid because they should be the opposite to each other's. So this is good. Now let's simulate our system for the initial state. Instead of 0, let's initialize it to be 1. So we can go back in here, double click the delay block, and then have the initial condition. The current state of the system is 1 instead of 0. Click enter or OK. And then now we can resimulate our system. So we can run the simulation from here or from here. It doesn't matter. So run. There you go. Now we're starting, the initial state of this system is 1. That's what we see. We're starting Q is 1. So what will be the next state? As we saw, from 0 to 8 seconds, the gate is disabled. So that's what we see here. The gate from 0 to 8 seconds, the gate is disabled. So we should hold the previous state of the system. That's what we see. From 0 and 8, Q is remaining 1 all the way. So now let's move when the gate is enabled at time equal 8 seconds. So we want to see the bottom 4 rows. When S is 0 and R is 0, we should hold the previous state of the system. In this scenario, the previous state is 1. That's what we see. From 8 to 10, it's remaining 1. What happened when S is 0 and R is 1? So the next state should go to 0. And that's what we see exactly between 10 and 12 seconds. The set is 0, and then the reset is 1. So the Q, the next state, is going from 1 to 0. Next, when set is 1 and reset is 0, so we're setting the next state to 1. And that's what we see also between 12 and 14 seconds. So it's going from 0 to 1 because the set is 1 and reset is 0. And then lastly, when both of them are enabled is our invalid state. And that's what we see here. Q and Q bar are the same, both 1, which is invalid because they should be the complement of each other. So that's what we see between 10 and 12. Q is 0, Q bar is 1. Between 12 and 14, we have Q is 1, Q bar is 0. So that's it. That system is working as expected and our circuit is working as intended. So at this step, we can move to designing the hardware because we ensure the system will work as we want. Thanks for watching. I hope this was helpful. If you have any questions, feel free to comment below and I can answer them. Thank you.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.